Hey everyone. We think we know how life works, but the way it actually started is completely wild. Today, Earth is covered in green plants and animals breathing air. But back then, it was just toxic gas and boiling lava. Here are four things that don't even sound real. First, life probably started in scalding hot acid at the bottom of the ocean. Second, the very first living things didn't even have DNA. Third, oxygen wasn't always a good thing. It was actually a deadly poison that caused a massive extinction. And fourth, every single living thing on Earth today comes from one specific microscopic blob. I'm just a guy reading stories, so subscribe if you want to stay. Also, where are you listening from tonight? Drop your city in the comments. Let's go back 4 billion years and see how it all began. So, 4 billion years ago, things weren't exactly peaceful. Imagine the space around our sun. It wasn't empty and quiet like it is now. It was more like a massive construction site where nobody was wearing a hard hat. You had these giant chunks of rock and metal just flying around at thousands of miles per hour. There was no order to it. Gravity was the only thing in charge, and it was a messy boss. It started pulling these pieces toward each other. When they hit, they didn't just bounce off. They smashed. They melted. They fused together into bigger and bigger lumps. This wasn't some slow, gentle process. It was violent. Every time a new rock hit the pile, it added more energy and more heat. Think about hitting a nail with a hammer. If you do it fast enough and hard enough, that nail gets hot to the touch. Now, imagine doing that with rocks the size of a mountain or a whole country. That's a lot of heat. Eventually, all that crashing and smashing turned the whole mess into a giant glowing ball. If you were looking at Earth back then from a distance, you wouldn't recognize it. It didn't have blue oceans or green forests. It looked like a dropped light bulb that was still glowing orange and white. Everything on the surface was liquid. We're talking about a planet-sized ocean of lava. There was no solid ground to stand on. If you tried to land a ship there, you'd just sink right into white-hot melted stone. The temperature was thousands of degrees. Nothing could live there. Not even the toughest germs or bacteria we know today could survive for a single second in that kind of heat. It was just a big, angry furnace floating in the dark. While all this was happening on the outside, something important was going on inside that ball of fire. The planet was sorting itself out. The heavy stuff, things like iron and nickel, started sinking toward the center. It fell right through the liquid rock until it reached the middle. The lighter stuff, the rocky material, stayed on top. It's a lot like how oil sits on top of water in a jar. This process gave the Earth its layers. It gave us the heavy metal core we have today. But even as the top started to try and cool down a tiny bit, the rest of space wouldn't leave it alone. The neighborhood was still incredibly crowded. There were millions of leftover rocks flying around, and they were all being pulled in by Earth's gravity. This is what people call the heavy bombardment. Think of it like a cosmic boxing match where Earth is the punching bag and it can't move out of the way. Huge asteroids, some of them bigger than a city, were constantly slamming into the surface. Every time the Earth tried to grow a skin, a thin crust of solid rock, another giant rock would come screaming in and blow it all to pieces. It was like trying to freeze a pond while a bunch of kids are constantly throwing bricks into it. The ice never gets a chance to stay solid for long. This went on for millions and millions of years. It wasn't just a bad day or a bad week. It was an entire era of total, non-stop destruction. These impacts were so big they could turn the whole surface back into a liquid state in an instant. The crust would start to harden, and then boom, another hit, another reset. Everything would melt again, and the clock would start over. And the air? You couldn't have breathed it, even if you could stand the heat. There was no oxygen back then. The sky wasn't blue. It was probably a thick, dusty red or a muddy brown. All those impacts and all that bubbling lava released a lot of gas from deep inside the planet. We're talking about steam, carbon dioxide, and other gases that would kill you the moment you took a breath. It was a toxic, suffocating soup. Between the flying space rocks, the liquid ground, and the poison air, early Earth was the most hostile place you can possibly imagine. It's actually hard to believe this is the same planet we're standing on right now. It took a massive amount of time for the chaos to finally start settling down. But before life could even think about getting a foothold, the planet had to stop trying to blow itself up every 5 minutes. The heat eventually started to bleed off into the cold of space. Slowly, and I mean really slowly, the surface began to win the battle. But it was a long, hard road to get from a ball of fire to something that could actually hold a drop of water. Our world started as a graveyard of rocks before it was ever a home for anything else. That's the starting point. That's the foundation. A hellish, glowing ball of fire that somehow had to turn into the blue marble we know today. So you have this giant, molten ball of lava floating in space. It is hot, it is angry, and it is basically the last place you would ever expect to find a drink of water. But here is the thing. We are sitting here today on a planet covered in the stuff. You look out at the ocean, and it seems like it has always been there, but it hasn't. So where did it come from? It's not like the Earth just grew a pair of lungs and breathed it out. It had to come from somewhere else. Think about space for a second. It is big, it is cold, and back then it was a total mess. It was like a cosmic shooting gallery. You had these giant chunks of rock and ice flying around everywhere at thousands of miles an hour. We call them asteroids and comets, but really they were just delivery trucks, and their cargo was water. See, further out in the solar system, where it was colder, these rocks weren't just dry dust. They were packed with ice. They were like frozen sponges. And for millions of years, they just kept slamming into us. Boom, boom, boom. It was a non-stop beating. Every time one of those things hit the Earth, the ice melted instantly. But since the ground was still glowing hot, that water didn't just sit there in a puddle. It turned straight into steam. You can imagine how thick and nasty that air was. It wasn't air you could breathe. It was just this heavy, choking blanket of water vapor wrapped around the whole planet. The Earth was basically a giant pressure cooker. It stayed like that for a long, long time. We are talking about millions of years of just steam and heat and rocks falling from the sky. It didn't look like a home. It looked like a disaster. But eventually, the hits started to slow down. The Earth started to lose some of that initial heat it had from when it was born. The surface began to harden up. It wasn't a liquid fire pit anymore. It was becoming a solid crust of dark rock. And as the surface cooled down, the air started to cool down too. That's when everything changed. You know that feeling when you have a cold soda on a hot day and the outside of the can gets all wet? That's condensation. That's exactly what happened to the entire planet. All that steam that had been trapped in the atmosphere finally started to cool off and turn back into liquid. And then it started to rain. I'm not talking about a summer storm that lasts 20 minutes. I'm talking about a rainstorm that lasted for thousands of years. Can you even picture that? Just endless, heavy, gray rain, day and night for centuries. It poured down from the sky, washing over the black rocks and filling up every single crack and crater on the surface. The low spots on the ground started to fill up first. Little ponds grew into lakes. Those lakes all ran together to form the very first oceans. It wasn't the beautiful, clear blue water you see on a postcard today, though. It was probably murky, salty, and full of minerals it had washed off the rocks. It was a giant, warm, chemical soup. But it was water, and it was everywhere. When the clouds finally broke and the sun hit the surface again, the planet looked completely different. It wasn't a glowing red ball anymore. It was a world of water. Most of the land was buried under miles of ocean. And that is the crazy part, if you really think about it. Most of the water in your sink, or in your coffee, or even inside your own body right now, it came from those space rocks. It has been here for billions of years, just recycling itself over and over again. It took a hellish beginning and a few million years of getting hit by space ice, but the Earth finally had its oceans. For the first time, the planet wasn't just a spinning rock. It was a place where things could actually happen. We had the water, and we had the heat coming up from the bottom of those new seas. The stage was finally set for the most important part of the story to begin. We had a world that was ready for life. So there we were. The planet was basically a giant, steaming pot of water sitting on a stove that never turned off. But if you think that water was anything like what you get out of your tap today, you're dead wrong. It wasn't clean. It wasn't clear. It was a thick, messy chemical soup. You had all these basic elements like carbon, hydrogen, and nitrogen just floating around in there. They were being pumped out of volcanoes and squeezed out of rocks. At first, they were just individual pieces, like a million tiny Lego bricks floating in a bathtub. They weren't doing much of anything yet. They were just bumping into each other and drifting away. The big question for a long time was how those little pieces started sticking together. You can't have a living thing if you don't have the parts to build it. It's like trying to build a car when you only have piles of iron and rubber. You need to turn that stuff into a piston or a tire first. For the longest time, scientists were stuck. They couldn't figure out how a dead planet full of simple chemicals could suddenly start making the complex parts needed for life. Some people thought it was a fluke. Others thought it might be impossible to ever prove how it happened. Then, in 1952, this young guy named Stanley Miller decided to step up. He was a graduate student at the University of Chicago, working with a famous chemist named Harold Urey. Miller had this idea that was pretty bold for the time. He didn't want to just talk about the early Earth. He wanted to build it. He wanted to see if he could take a bunch of dead gas and water and spark it into something more. So he and Urey got to work in their lab. They didn't have any fancy computers or high-tech sensors. They just had glass. They built this strange-looking contraption made of glass tubes and flasks. It looked like something a mad scientist would use. In one glass ball at the bottom, they put some water. That was their ocean. In another part of the machine, they filled the tubes with a specific mix of gases. They used methane, ammonia, and hydrogen. Back then, they figured that was what the early Earth felt like. It would have smelled terrible, like a mix of window cleaner and rotting eggs. There was no oxygen in there because, remember, there were no plants or trees yet to make it. It was a suffocating, nasty environment. Now, Miller knew that just letting these gases sit there wasn't going to do anything. He needed a kickstart. He needed energy. On the early Earth, that energy came from a few places, but one of the biggest was lightning. The sky back then was probably a non-stop light show of massive storms. So Miller took 2 metal electrodes and stuck them right into the glass flask filled with gas. He was going to shoot electricity straight through it to see what would happen. He started the experiment by heating the water at the bottom. The water turned into steam and started traveling up through the glass tubes, mixing with those stinky gases. Once the steam and gas were all swirled together, Miller turned on the power. He started zapping that mixture with constant sparks of electricity. Pop, pop, pop. It was like a miniature lightning storm trapped in a bottle. Then the steam would travel further down the tube where it was cooled off, turning back into liquid water that dripped back down into the starting flask. It was a loop, a perfect little cycle of weather, just like on the real Earth. Miller let this machine run. He didn't just do it for an hour or two. He let it run for a whole week. At the end of the first day, the water in the flask started to change color. It wasn't clear anymore. It turned a weird pale pink. By the end of the week, the water had turned a deep, murky red. It looked like a muddy pond. Something had definitely changed. The simple gases and the clear water were gone. In their place was this dark chemical sludge. Miller and Urey took a sample of that red water and ran some tests. What they found blew the doors off the scientific world. They didn't find life, not yet, but they found amino acids. Now, if you aren't a biology nerd, that might not sound like a big deal, but it's huge. Amino acids are the building blocks. Every single bit of your body, your hair, your skin, your heart, your brain, is made of proteins, and every protein is just a long chain of amino acids. Before this experiment, people thought you needed a living body to make amino acids. They thought it was something only life could produce. But Miller proved that was wrong. He showed that if you have the right gases, some water, and a little bit of a spark, the chemistry happens all by itself. You don't need a miracle. You just need a storm and a little bit of time. Those basic elements that were floating around in the ocean didn't stay basic for long. The lightning was hitting the water and the air, and it was forcing those atoms to hold hands and stay together. This was the first time anyone had ever proven that the chemical soup theory actually worked. It showed that the early ocean wasn't just a place where life could live. It was a factory that was actively building the parts for life. You can imagine the whole planet's surface at this time. You've got these massive oceans under a dark purple sky. There are no birds, no fish, not even a single blade of grass. It's just water and rock. But inside that water, things are getting complicated. Every time a bolt of lightning hit the sea, it was like a master chef adding ingredients to a pot. The water was getting thicker with these amino acids. They were floating around by the trillions, bumping into each other in the warm currents. They were starting to collect in little pools and along the edges of the shore. The planet was basically stocking up. It was filling its pantry with all the supplies it was going to need for the next big step. Miller and Urey's experiment didn't solve everything, of course. Making the bricks isn't the same thing as building the house. Just because you have a pile of amino acids doesn't mean you have a cell that can eat and grow and reproduce. But for the first time, we had a map. We knew that the transition from a dead rock to a living world started with a simple spark in a messy soup. It wasn't magic. It was just the way the universe worked when things got hot and crowded. You can almost picture Stanley Miller looking at that red water in his lab and realizing what he'd done. He had found the recipe. He'd shown that the world was capable of creating the ingredients for life out of thin air and dirty water. The stage wasn't just set anymore. The actors were starting to show up. They were small and they were simple, but they were there. And they were ready to start the longest, most incredible show in the history of the world. All those chemicals were floating in the waves, waiting for the next big change to pull them together into something that could finally breathe. So there we were, a planet-sized soup of chemicals just sloshing around in the waves. Everything needed for life was right there, but it was all just floating. It wasn't doing anything yet. It was like having all the parts for a car spread out across a giant parking lot. You have the wheels over here, the engine over there, and the seats in the corner. But if they just sit there, you don't have a car. You just have a mess. To get things moving, you need a set of instructions. You need a way to tell those parts how to get together, and more importantly, how to make more cars. Today, every living thing on Earth uses DNA for that. You've heard of it. It's that famous double helix shape that looks like a twisted ladder. It's the master blueprint for everything, from a blade of grass to your annoying cousin. But here's the problem. DNA is incredibly complicated. It's like a high-tech computer chip. There is absolutely no way the early Earth just woke up one day and built a computer chip from scratch. It's too fragile, and it needs a whole team of specialized proteins to even work. It's a classic chicken and the egg situation. You need DNA to make proteins, but you need proteins to manage the DNA. So, how did we get around that? Well, the answer is a scrappy little molecule called RNA. If DNA is a fancy gold-plated hard drive kept in a climate-controlled room, RNA is like a crumpled-up note written in pencil. It's much simpler. It's usually just a single strand instead of a double one. But don't let that fool you. In the early days of Earth, RNA was the absolute king of the puddle. Scientists call this the RNA world. It was a time before cells, before bacteria, and long before anything had a face. Think about those chemicals floating in the water. Among all that junk, long chains of RNA started to form. Now, this didn't happen because some invisible hand put them together. It happened because of basic chemistry. RNA is made of 4 main building blocks. Let's just call them letters. In the water, there were millions of these loose letters drifting around. Here is where the magic happens. These letters are naturally sticky, but they're picky about who they stick to. One letter always wants to grab on to its specific partner. It's like a magnet. If a strand of RNA is floating through the water and it has a specific sequence of letters, it acts like a template. Loose letters in the water start bumping into it. If a letter finds its partner on the strand, it clicks into place. Imagine a long line of people holding hands. Now imagine a crowd of people walking past them. If someone in the crowd sees their best friend in the line, they grab their other hand and stay there. Pretty soon, you have a second line forming right next to the first one. This is how RNA started copying itself. It was a total accident of chemistry. A strand would float into a warm tide pool, collect a bunch of partners, and form a twin. Then maybe the sun would come out and heat the water up. That heat would make the two strands wiggle until they peeled apart. Now, instead of one strand, you had two. When the water cooled back down, those two strands would each start grabbing new partners again. 2 became 4, 4 became 8. It wasn't alive, not really. It didn't have a brain or a heart. It was just a chemical that was really good at making more of itself. But it gets even better. Because this was a messy, natural process, it wasn't perfect. Sometimes, while a strand was grabbing partners from the water, it would grab the wrong letter. It's like a typo in a text message. Most of the time, this typo didn't matter, or it made the strand fall apart. But every once in a while, a typo actually made the RNA strand better at its job. Maybe the new shape of the strand helped it grab letters faster. Maybe it made the strand tougher so it didn't break as easily in the rough waves. This was the very first version of competition. These RNA strands were fighting for the building blocks in the water. There wasn't an infinite supply of those letters. If you were an RNA strand that was fast at copying yourself, you'd use up all the nearby supplies. The slow strands would eventually just break down and disappear. You see what happened there? That's evolution. It started before there were even animals. It was just molecules trying to outcompete each other. I want you to really picture this scene. It's a world of gray rocks and black sand. There are no trees, no birds, nothing, just the sound of the wind and the crashing waves. And in these little pockets of water along the shore, millions of these invisible chains are busy at work. They are bumping, sticking, peeling apart, and doing it all over again. They were like little chemical engines that wouldn't stop. Some of these RNA strands got so good at this that they started doing more than just copying. Their shapes allowed them to actually chop other molecules apart or stitch them together. They started acting like little tools. They were building things. They were changing the environment around them to make it easier to keep copying. This went on for millions of years. It wasn't a fast process. It was a slow, grinding game of trial and error. Trillions of strands failed. They fell apart. They got washed out to sea, where they just didn't work. But the ones that survived were the best of the best. They were the ancestors of everything. Eventually, these RNA strands started getting more protective. They didn't want to just float out in the open, where they could get smashed by a rock or burned by the sun. They needed a container. They needed a house. While all this RNA copying was going on, there was another type of molecule floating in the water: fats. You know how when you put oil in water, it forms little bubbles? Well, the early ocean was full of those oily, fatty bubbles. And every now and then, an RNA strand would get lucky. It would find itself trapped inside one of those bubbles. Suddenly, it had a wall. It had a shield that kept its building blocks close and kept the dangerous stuff out. This wasn't just a strand of chemicals anymore. It was starting to look like a package. It was the very first, most basic version of a cell. Inside these little fatty bubbles, the RNA could work even faster. It didn't have to wait for a random letter to float by in the giant ocean. It had a concentrated supply right there inside the bubble with it. This was a massive upgrade. It was like moving from a campfire in the middle of a forest into a kitchen with a pantry. But as great as RNA was, it had its limits. It was a bit too unstable. It was great for a quick note, but if you wanted to build something really big, something like a tree or a human, you needed a better way to store that information. You needed something that wouldn't fall apart the second the water got a little too hot. That's when the RNA started to change. It started to evolve into something more permanent. It began to store its secrets in a new, more durable format. It was moving away from the messy handwritten notes and starting to write the master book of life. The RNA world was coming to an end, and the age of DNA was about to begin. But it all started with those simple strands bumping into each other in the dark, just trying to make a copy. So those RNA strands were just floating there. They were doing their best to copy themselves, but it was a tough job. Imagine you're trying to build a complicated Lego set in the middle of a crowded swimming pool. Every time you find the piece you need, a wave knocks it out of your hand. It's frustrating, it's slow, and honestly, it's a miracle it worked at all. For life to really get going, it needed a way to keep its stuff together. It needed a bag, a box, a room. It needed a home where those pieces wouldn't just float away. This is where the fat comes in. Now, when I say fat, don't think about a steak or a piece of butter. Think about oil. You've seen this 1,000 times in your kitchen. You drop a bit of oil into a glass of water, and it doesn't just disappear. It doesn't mix. Instead, it stays in these little round beads. That happens because of how these molecules are built. One end of the molecule is a total water lover. It wants to hang out with water all day. But the other end, it hates water. It's terrified of it. It'll do anything to stay dry. Because of that weird setup, these fat molecules have a clever trick. When they're in water, they can't just stay as single pieces. They find each other and huddle up. They turn their water-hating tails inward toward each other, and they keep their water-loving heads on the outside. It's like a group of people in a huddle during a rainstorm, trying to keep the dry stuff in the middle. This huddle naturally forms a circle, and if you have enough of those molecules, they form a hollow ball, a tiny microscopic bubble. These little bubbles were everywhere in the early ocean. Thousands of them, millions of them, just drifting around. They were popping and forming and bumping into things near the heat of those underwater vents or along the edges of muddy tide pools. They were just empty containers floating around with no real purpose. But the world was about to get a lot more interesting. Think back to those RNA strands I mentioned. They're still floating around in the same water, still trying to make copies of themselves. Every now and then, a fat bubble would form right on top of an RNA strand, or maybe a strand would get shoved inside a bubble during a splash or a sudden shift in the water. Suddenly, that piece of RNA wasn't alone in the big, scary ocean anymore. It had a wall. It had a border. It had its very first room. This was a massive game changer. You see, once you're inside that little bubble, things get crowded. And in the world of early life, crowded is exactly what you want. When you have all your building blocks trapped in one small space, you don't have to go looking for them. They can't just drift off into the dark. They're right there with you. The RNA could copy itself much faster because the pieces it needed were bouncing off the walls of the bubble, landing right where they needed to be. It was like going from that chaotic swimming pool to a small, organized workshop where all your tools are within arm's reach. But there's an even bigger reason why these fat bubbles mattered. They started a kind of competition. You see, these bubbles weren't all the same. Some were made of better fats that held together longer. Some were a bit leaky, which was actually a good thing. A leaky bubble allowed the small chemical building blocks from the outside water to seep in, but it was too tight for the big RNA strands to get out. It was a one-way street for food. If a bubble happened to catch a piece of RNA that was really good at making copies, that RNA would start to fill up the space. As it made more and more of itself, it started to put pressure on the bubble from the inside. The bubble had to grow to keep up. It would grab more fat molecules from the surrounding water, pulling them in to make its wall bigger. Eventually, the bubble would get so big and so unstable that it couldn't hold its shape anymore. It would pinch in the middle, wiggle around, and then snap. It would pop into two separate bubbles. And because the RNA inside had been busy making copies, both of those new bubbles now had their own set of instructions. This wasn't just a chemical reaction anymore. It was reproduction. 1 became 2. 2 became 4. The cycle was officially moving. The wall also acted as a shield. The early Earth was a pretty violent place. The ocean was full of harsh chemicals, huge changes in salt levels, and wild swings in temperature. Any of those things could easily rip a naked RNA strand apart. But inside the bubble, the RNA was safe. It was protected from the chaos outside. This safety allowed the RNA to get more complex. It could start to experiment with its own code. It could start to build better tools for itself because it wasn't constantly being broken down by the environment. I want you to really think about what that means. This right here is the very first cell. It wasn't much to look at. It didn't have a brain or a heart or any of the fancy parts we think of when we think of life today. It was just a little bit of genetic code trapped inside a greasy bubble. But it was the blueprint for everything. It was the start of the us and them of the universe. On the outside of that fat wall, it was just physics and chemistry. It was just rocks and wind and dead water. But on the inside, it was a system. It was a unit that wanted to keep existing. It was a little engine that was eating, growing, and splitting. For the first time in the history of the planet, there was a clear line between the living and the non-living. Once life had a container, the pace of everything changed. It wasn't just about random luck anymore. It was about survival of the best bubble. If your fat wall was stronger, you stayed alive. If your RNA was faster at making copies, your family took over the puddle. The walls didn't just hold life in. They kept the rest of the world out. They gave life the privacy it needed to turn into something truly incredible. This tiny, oily bubble was the ancestor of every single thing you've ever seen alive, from the birds in the sky, to the trees in the park, to the person sitting next to you. We are all just extremely complicated versions of that first little grease bubble that refused to let its parts float away. It's a simple start, but it was enough to change the world forever. So there you are. You're a tiny grease bubble floating in a massive, ancient ocean. You've got your outer skin, and you've got your little pile of instructions inside. You're officially the most basic form of life on the planet. But there is a huge problem. The world around you is trying to kill you every single second. Back then, the surface of the Earth wasn't a nice place for a vacation. It was a total war zone. If you were floating on the top of the water, you were basically a sitting duck. Why? Because the sky was literally falling. For millions of years, giant rocks from space were slamming into the Earth. We aren't talking about little shooting stars. We're talking about asteroids the size of cities. They were hitting the ocean so hard that they would turn the top few hundred feet of water into steam instantly. If you were a little grease bubble caught in that, you were toast. You'd be boiled alive before you even had a chance to divide. And it wasn't just the space rocks. The sun was a problem too. Today we have a nice ozone layer that acts like a pair of sunglasses for the planet. It keeps out the worst of the radiation. But back then, that layer didn't exist yet. The sun was blasting the surface with raw, deadly rays. If the heat didn't get you, the radiation would rip your little chemical instructions apart. The surface was a death trap. So life had to find a hideout. It needed a place where the asteroids couldn't reach it and the sun couldn't burn it. It needed a basement. And that's when everything changed. These little bubbles started to sink. They drifted down, away from the waves, away from the light, and away from the chaos. They kept going down until the water above them was miles deep. Down there, the water is heavy. It creates a massive shield. An asteroid could hit the surface and cause a global firestorm, but a few miles down, you wouldn't even feel the vibration. It was the only safe place left. But there's a new problem once you get down there. It's freezing cold and it's pitch black. Life needs energy to keep going. It's like a car that needs gas or a phone that needs a battery. Up at the top you have the sun, but down in the deep there's nothing. Or at least that's what it looks like at first. If you keep going all the way to the very bottom, you find something incredible. You find these giant towers of rock sticking out of the floor. They look like chimneys, and they're spitting out thick black clouds. It looks like smoke, but it's actually superheated water packed with minerals. These are hydrothermal vents. They're basically cracks in the Earth's crust where the internal heat of the planet leaks out. Think of it like the plumbing in an old house. Cold seawater seeps down into the cracks in the ocean floor. It goes deep down where the rocks are glowing hot from the Earth's core. That water gets cooked. It gets so hot that it should be steam, but the weight of the ocean above it keeps it liquid. As it heats up, it dissolves all sorts of metals and chemicals from the rocks. Then it shoots back up through the floor like a geyser. When that hot chemical soup hits the freezing cold ocean water, the minerals turn solid. They build up these tall, jagged chimneys.
Some are as tall as a 10-story building. And this, right here, was the perfect kitchen for the first life forms. This place had everything. It had heat, which provided the energy life needed to stay active. It had a constant supply of chemicals, which acted like food. And most importantly, it had a weird kind of structure. These chimneys weren't just solid rock. If you looked at them under a microscope, you'd see they were full of tiny little holes. They were like giant sponges made of stone. For our little grease bubbles, these holes were like move-in ready apartments. A bubble could drift into a hole and stay there. It wouldn't get washed away by the currents. It was protected. It had a warm wall on one side and a constant stream of food flowing past it. It was the first stable neighborhood in the history of the world. Inside these tiny rocky rooms, the chemistry of life started to get way more interesting. Because the vents were pumping out a very specific mix of stuff, it created a sort of natural battery. You had high-energy chemicals on the inside of the chimney and low-energy water on the outside. Life figured out how to sit right in the middle of that flow. It used that difference in energy to power itself. It's the same basic trick your own cells use right now to keep your heart beating. You're basically running on the same battery tech that was invented at the bottom of the ocean 4 billion years ago. It wasn't a fast process. This wasn't a lightning strikes and suddenly there's a fish kind of situation. It was slow. It was millions of years of chemistry bumping into other chemistry. But because these vents stayed active for centuries at a time, life had the one thing it needed most: time. It had time to practice. It had time to get better at making copies of itself. It had time to figure out how to build better walls and better engines. In these dark, hot corners of the ocean, the grease bubbles stopped just existing and started living. They started to cooperate. They started to use the minerals from the vents to build their own internal machinery. They turned from simple bags of oil into little chemical factories. While the surface of the Earth was still being pummeled by space rocks and scorched by the sun, the deep ocean was quiet. It was a laboratory. It was a place where the ingredients of life could be stirred together in just the right way. Without these vents, life probably would have been wiped out as soon as it started. Every time a big rock hit the planet, the reset button would have been pushed. But the vents were the ultimate bunker. You can think of the vents as the cradle. They provided the warmth, the food, and the protection. They were the only place on the planet that wasn't a nightmare. And because of that, life didn't just survive. It started to thrive. It grew into the cracks. It coated the rocks. It turned the bottom of the ocean into a living, breathing landscape long before the first patch of green ever appeared on land. It's kind of funny when you think about it. We usually think of life as something that needs the sun and the air, but we started in the one place that had neither.
We started in the dark, under miles of crushing water, huddled around a hole in the ground that smelled like rotten eggs and spit out boiling liquid. It's not the most romantic beginning, but it worked. It gave us a foothold. And once life had a foothold, it wasn't going to let go. It was going to keep pushing, keep changing, and eventually it was going to find a way to leave the basement and take over the rest of the house. But for a very long time, those vents were the entire world. They were the only spot in the universe, as far as we know, where things were getting more complicated instead of falling apart. That little grease bubble had finally found a home, and from that home it was about to start an explosion of growth that nothing, not even city-sized asteroids, could stop. So that little grease bubble survived. It stayed put. It found a place where it could actually exist without getting ripped apart by the tide or cooked by the sun. But I want you to understand something. This wasn't a solo act. It wasn't like one single cell showed up and said, "All right, I'm the boss." It was way messier than that. Think about a crowded parking lot full of old, beat-up cars. They're all different makes and models. Some have 3 wheels, some have engines that barely turn over, some don't even have doors. That's what the bottom of the ocean looked like back then. There were millions of these tiny experiments happening at the same time. These weren't quite what we would call life yet, but they were trying their best. They were just little chemical bags floating around, picking up bits of energy from the heat leaking out of the earth. You had all these different versions of what life could be. Some used one set of chemicals, others used something completely different. It was like a giant laboratory where nobody knew the rules. Most of these experiments failed. They'd pop, they'd run out of food, they'd get crushed. I want you to really picture this world. It's dark, it's heavy. The pressure of the ocean above you is enough to crush a steel pipe like a soda can. And in these tiny little cracks in the rock, life is trying to find a foothold. It's not just one cell. There are trillions of them. Most of them are dead ends. They're like those old computer programs that crash the second you try to open them. They had some of the parts, but they didn't have the whole package. One cell might have been great at staying stable, but terrible at getting food. Another might have been great at getting food, but it would fall apart every time the water temperature changed by a degree. It was a giant, chaotic mess of almost life. In that crowd, there were a few that were just a little bit better at staying together. They were a little better at pulling in fuel. They were a little better at making copies of themselves. Because that's the real trick, right? You can't just exist. You have to be able to make a version 2 of yourself. If you can't do that, you're just a rock with extra steps. Eventually, the field started to narrow down, and this brings us to the main character of our story. Scientists have a name for this specific winner. They call it LUCA. It stands for the last universal common ancestor. But honestly, let's just think of it as the great-great-grandfather of everything that has ever lived. Now, LUCA wasn't the first cell to ever exist. I want to be really clear about that. There were probably thousands of ancestors before it, and millions of neighbors living right next door. But LUCA is the one that actually made it. It's the one that didn't die out. It's the survivor. Think of it like a family tree where a huge storm comes through and knocks down almost every single branch on the tree. LUCA is the one branch that didn't snap. It stayed attached. What made LUCA so special? It wasn't some supercell. It didn't have a brain. It didn't have eyes. It was just a tiny microscopic speck. But it had the right instruction manual. It had a way to store information. It figured out how to take the stuff around it, the minerals, the heat, the gases, and turn that into more of itself. It was the first one to really master the art of the copy-paste. Every time it split in two, it passed down its secrets, and those secrets were so good that they still work today. Think of it like a relay race where every runner before LUCA dropped the baton. They ran fast, sure, but they never passed the stick. LUCA was the first one to grab that baton and actually hand it to the next runner, and then that runner handed it to the next one. That baton is the code for life. It's the set of instructions that tells a cell how to be a cell. And that relay race has been going on for 4 billion years without a single person dropping the stick. This is the part that usually blows people's minds when I tell them. Every single thing you see outside your window right now came from that one specific cell. I'm not talking about some vague idea. I'm talking about a direct line. That oak tree in your yard, it's your cousin. That fly you swatted this morning, also your cousin. The mold on the bread you forgot to eat, yep, related. You can trace your family history back through your parents, your grandparents, through thousands of years of humans, then monkeys, then fish, all the way back to this one tiny bubble at the bottom of a dark, hot ocean 4 billion years ago. When you look at a blade of grass, you are looking at a relative. When you see a blue whale swimming in the ocean, you are looking at a distant brother. We all share the same basic chemistry. We all use the same basic way to turn food into energy. We all use the same kind of code to build our bodies. If you look deep enough into the cells of a mushroom or a tiger, you will find the fingerprints of LUCA. It's all there. It's the same engine, just inside a different car. I think we sometimes forget how lucky we are that LUCA was so tough. The early Earth was a nightmare. It was a place of fire and acid and falling rocks. There were times when the entire ocean might have boiled. There were times when the whole planet froze over. But LUCA's family line never quit. It moved. It adapted. It hid in the deep places when the surface was too dangerous. It learned how to eat different things. It learned how to live in the cold and the heat. It was the ultimate survivor. If LUCA had died, if that one little bubble had popped before it could split, none of this would be here. No grass, no dogs, no you, no me. We are all just different versions of that one original blueprint. We've changed a lot, obviously. We grew legs and lungs and big brains. We learned how to build skyscrapers and fly to the moon. But at the very center of every single cell in your body, there is a piece of code that has been running non-stop for billions of years. It's the same code that was running inside LUCA. It's a chain that has never been broken, not once, through volcanoes, through ice ages, through asteroids that wiped out the dinosaurs. That little flame kept burning. It's the most successful thing in the history of the universe. And it all started with one lucky survivor in a world full of failures. I want you to think about that next time you feel small. You come from a line of winners that stretches back to the very beginning of time. You are part of the one group that didn't give up. Out of all those millions of different types of cells that were floating around those vents, yours is the only one that made it to the finish line. Every other line of life died out. They reached a dead end. But your ancestors just kept going. They saw the worst the universe could throw at them, and they just kept making copies. They kept the story going. And because they did, the world went from a silent rock in space to a place filled with billions of different voices. All of them started from that one single point. All of them started with LUCA. So LUCA was the start. It was the first thing that really worked. But here is the thing about LUCA. Even though it was our great billion times great-grandparent, it was kind of a mess. It had a huge problem that almost ended the whole story before it even got to the good parts. That problem was its memory. Think about it like this. If you want to build a house, you need a set of blueprints. You need to know where the pipes go, where the wires run, and where to put the front door. If you lose those blueprints, or if the ink smudges and you can't read them, you're in trouble. You might end up putting a toilet in the middle of the kitchen. Early life was trying to build itself using a molecule called RNA. And RNA is basically a blueprint written on a cheap paper towel in the middle of a rainstorm. See, RNA was the original do-it-all tool. It was the first molecule that could actually store information and do physical work at the same time. It was the scout, the architect, and the construction worker all rolled into one. In the beginning, that was a huge advantage. Life didn't have to wait for a bunch of different parts to show up. RNA just did the job. But as life started to get a little bit more complicated, that one-man show approach started to fall apart. The issue is that RNA is very fragile. It's a single strand of code. It's thin, it's flimsy, and it's very reactive. Back then, the world was a violent place. It was hot, it was full of radiation, and there were nasty chemicals floating around everywhere. Every time an RNA molecule tried to copy itself so a cell could split and grow, something went wrong. A piece would snap off. A chemical would bump into it and change a letter of the code. Heat would shake the whole thing apart. Imagine you're trying to copy a long book by hand, but every 5 minutes someone shakes the table or spills coffee on the page. Pretty soon the story doesn't make any sense. The words get scrambled. In the world of early life, a scrambled code means a dead cell. If the instructions for how to eat or how to move get deleted, that's it, game over. For a long time, life was stuck in this loop. It would take 1 step forward and 2 steps back because its instruction manual kept getting ruined. This is where the big upgrade happened. It wasn't like some scientist sat down and designed a better system. It happened the way everything in the early world happened, by a total accident. Some of these early cells started to have mutations. Now, most mutations are bad. They usually break things. But every once in a while, a mistake actually fixes a problem. One of those mistakes involved a slight chemical change to the RNA. It lost an oxygen atom. That sounds like a small thing, but it changed everything. It made the molecule less reactive. It made it tougher. And then another massive thing happened. Instead of staying as a single lonely strand that could break at any moment, this new version of the code found a partner. It zipped itself together with a mirror image of itself. This was the birth of DNA. When you look at DNA, you see that famous twisted ladder shape. That shape isn't just for show. It's a genius bit of engineering. By zipping two strands together, life created a backup system. If one side of the ladder gets damaged or hit by a bit of radiation, the other side still has the information. It's like having two copies of your house keys instead of one. If you lose one, you aren't locked out. But it's even better than that. Think of DNA like a high-end, double-locked hard drive. It's stable, it's sturdy, it doesn't just fall apart when things get a little warm. Because it's so much tougher than RNA, it can hold way more information. Life could suddenly write much longer books. It could store instructions for things that RNA could never dream of. It could build bigger cells, more complex engines, and better ways to survive. Now, life didn't just throw away RNA. That would be like throwing away your hammer just because you bought a better toolbox. Instead, life gave them different jobs. The DNA stayed safe inside the center of the cell, locked away like a set of original blueprints in a fireproof safe. When the cell needed to actually build something, it would make a temporary copy of a small part of that DNA using RNA. It would take the instructions out into the cell, get the job done, and then it would break down and get recycled. If the RNA work order got ruined or smudged, it didn't matter. The cell could just go back to the DNA and print a fresh copy. This switch was the moment life really took off. Before DNA, life was like a business that kept losing its files every single night. It couldn't grow because it couldn't remember how it did things the day before. Once DNA showed up, life finally had a permanent memory. It could build on its successes. It could save the files for how to breathe, how to turn sunlight into food, or how to move through the water. And it could pass those files down to the next generation without them getting corrupted. You and I are walking around today because of this exact change. Every single cell in your body is running on this same system. You have about 2 meters of DNA stuffed into almost every cell you own. It's all coiled up, packed tight, and locked down. It's the same hard drive that those early cells figured out billions of years ago. It's pretty wild when you think about it. We think of ourselves as these incredibly complex beings, but at the core, we are just a very long, very successful chain of data. We are the result of a lucky break where a flimsy piece of code decided to double up and protect itself. Without that switch, from the fragile paper towel of RNA to the heavy-duty hard drive of DNA, life would have stayed as a tiny invisible smear on the rocks. It never would have had the stability to build a heart or a brain or a hand. It needed that safety. Once the instructions were safe, the real building could begin. The world was no longer just about surviving the next 5 minutes. It was about the long game. It was about taking those instructions and seeing just how far they could go. And as it turns out, they could go a lot farther than anyone could have guessed. They were about to build things that would change the entire face of the planet. But to do that, they had to work together. They had to take those saved instructions and use them to turn a bunch of individual parts into a team. That was the next big hurdle, and it was going to change the world forever. So now you've got these teams. They're functional, they're organized, and they're ready to take on the world. But there's a massive problem that no one saw coming. It's the same problem every living thing has faced since the beginning of time. You need fuel. You need a way to keep the lights on. Think about it like this. You can have the best, most high-tech factory on the planet, but if you don't have a power cord plugged into the wall, that factory is just a giant, expensive paperweight. It doesn't do anything. It just sits there. Those first little teams of cells were in that exact spot. They had their instructions and they had their parts, but they were running on fumes. At first, it wasn't a huge deal. The early Earth was basically a giant bowl of free soup. You had volcanoes venting all sorts of nasty-smelling chemicals into the water. You had minerals dissolving off the rocks. To us, that sounds like a toxic nightmare, but to a brand new cell, that was a five-star buffet. These cells just floated around and bumped into these chemicals. They'd pull them inside, break them apart, and use the energy that held those molecules together to power their own little systems. It was easy. It was effortless. For a while, life was just one big free lunch. But there's a catch with free lunches. They never last. These cells were getting really good at making copies of themselves. That was their whole job, right? Follow the instructions, build a copy, and split. One cell became 2, 2 became 4, 4 became 8. Before you know it, you have billions and billions of these things floating in the water. They were everywhere, and every single one of them was hungry. Every single one of them was grabbing those free chemicals out of the water as fast as they could. You can probably guess what happened next. The soup started to run thin. It's like being at a party where there's only one bowl of chips. If it's just you and a friend, you can snack all night. But if 100 people show up, that bowl is going to be empty in 5 minutes. The Earth couldn't keep up. The volcanoes and the rocks weren't pumping out chemicals fast enough to feed the growing crowd. Life had hit its first real wall. This was the first energy crisis, and it was a total disaster. Cells started to starve. They were literally running out of the basic stuff they needed to stay alive. If nothing changed, the whole story of life would have ended right there, at the bottom of a lukewarm ocean, because everyone ran out of food. It was a race against time. The cells that couldn't find a new way to get energy were simply dying off. The competition was brutal. If you weren't the fastest to grab a molecule of sulfur or iron, you were done. All of this went on for a long time. It was a slow-motion catastrophe. But then one specific group of cells stumbled onto a solution that was so weird and so brilliant, it changed the entire planet forever. We call these guys cyanobacteria. You've probably seen them before. They're that green scum you see on the top of a pond when the water hasn't moved in a while. They don't look like much. They don't look like world changers, but they are the reason you are here today. These cyanobacteria did something that no other living thing had ever done. They stopped looking for food in the water. They stopped waiting for the volcanoes to spit out something they could eat. Instead, they looked up. They noticed that there was this massive glowing ball of fire in the sky that was hitting the ocean with a constant stream of energy. They figured out how to tap into the sun. Now, think about how crazy that is. Before this, every bit of energy life used came from the Earth itself. It was limited. It was hard to find. But the sun is huge. The sun is consistent. And most importantly, the sun is free. These cyanobacteria developed a way to catch those rays of light and use that energy to power their internal factories. They didn't need the chemical soup anymore. They just needed a little bit of water and a lot of sunlight. We have a fancy name for this now. We call it photosynthesis. But don't let the big word trip you up. It's just a way of turning light into bread. These cells built their own internal solar panels. When a beam of light hit the cell, it triggered a chain reaction. The cell would use that light energy to rip apart water molecules. It would take the pieces it needed to make sugar, which is basically high-grade cell fuel. This was a total game changer. It was like moving from a world where everyone had to hunt for scraps in the trash to a world where everyone had a personal chef who worked for free. Suddenly, the energy crisis was over. The cyanobacteria didn't have to fight over a limited supply of chemicals. They could live anywhere the sun touched the water. And since the sun touches pretty much the whole surface of the ocean, their territory became massive. They started to multiply like crazy. They spread across the globe in a giant green wave. They were so successful that they started to physically change the ocean. Because they were using sunlight and water to make their own food, they didn't need to stay near the deep-sea vents or the volcanic cracks in the Earth's crust. They could float right on the surface. They were the first creatures to really take over the world. But there was a side effect to this new solar-powered lifestyle. When these cyanobacteria ripped apart water molecules to get the parts they needed, they had some leftover scraps. Specifically, they had a lot of leftover oxygen. To the cyanobacteria, oxygen was just trash. It was a waste product. They didn't want it, so they just dumped it out into the water. At first, this didn't seem like a big deal. The oxygen would just react with iron in the water and sink to the bottom as rust. But there were so many of these green cells, and they were working so hard that they started producing more oxygen than the ocean could handle. It started bubbling up out of the water and into the air. This was a massive shift. Before this, the air on Earth didn't have much oxygen in it at all. It was mostly nitrogen and carbon dioxide. It would have been impossible for us to breathe. But these tiny green cells were slowly, steadily filling the atmosphere with this brand new gas. They were literally rebuilding the world's atmosphere from scratch, one bubble at a time. It's hard to overstate how important this was. By figuring out how to eat sunlight, cyanobacteria didn't just save life from starving to death. They provided the spark for everything that came next. They created a world where there was plenty of energy to go around. They proved that life didn't have to just take what the Earth gave it. Life could find a new way. It could innovate. It could tap into the power of the stars. So, the next time you see a patch of green moss or some pond scum, give it a little credit. Those tiny cells were the ones who saw the energy crisis coming and didn't give up. They didn't just sit there and wait to go extinct. They looked at the sun and thought, I can use that. They turned a disaster into the greatest success story in history. They took the raw power of the universe and used it to fuel the future. And that future was about to get a lot more complicated. So we left off with life figuring out how to stay alive. But the truth is, life had a massive energy problem. It was basically living paycheck to paycheck. It was stuck down in those deep-sea vents, eating whatever chemicals the Earth happened to burp up. If the vents stopped smoking, the life around it died. It was a dead-end job. Life was hanging on by a thread, and if it wanted to actually go somewhere, it needed a better way to get paid. It needed a new source of power that wouldn't run out. And that power was right above its head, the sun. Think about the sun for a second. It is this giant, screaming ball of fire in the sky that dumps a ridiculous amount of energy onto the planet every single second. For millions of years, that energy just hit the rocks and the water and went to waste. Nobody knew how to catch it. It's like having $1 billion sitting in a bank account right in front of you, but you don't have the PIN code to get the cash out. Life was starving in the middle of a feast. But then, a few tiny, single-celled creatures called cyanobacteria finally cracked the code. They figured out how to build the world's first solar panels. These things were microscopic, but they were about to change the entire chemistry of the planet. They didn't have brains or eyes or hands, but they were the smartest engineers the world had ever seen. I want you to imagine these bacteria like little green factories. They weren't just floating around aimlessly anymore. They were working. To get their factory running, they needed 3 specific ingredients. They needed sunlight, they needed water, and they needed carbon dioxide. Now, you might think, okay, those things are everywhere. And you're right, that was the genius of it. Instead of waiting for a rare chemical from a volcano, they used the stuff that the world was literally made of. Here is how the factory actually worked. First, they had this special green pigment inside them called chlorophyll. You've seen this stuff a million times. It's why grass is green and why trees are green. But back then, it was brand new tech. This chlorophyll acted like a net. When a ray of light hit the bacteria, the chlorophyll would snag those light particles and hold on to them. This gave the bacteria a tiny jolt of electricity. It was the spark they needed to turn the machines on. But having power isn't the same as having food. You can't eat a bolt of lightning. You have to use that energy to build something you can actually use. So the bacteria took that solar energy and used it like a sledgehammer. They pointed that energy at water molecules. Now, water is pretty tough. It's made of 2 hydrogen atoms stuck to 1 oxygen atom, and they really like being together. They don't just fall apart on their own. It takes a lot of force to break them. But the cyanobacteria used that sunlight to bash the water molecules apart. They ripped the hydrogen away from the oxygen. This was the heist of the century. They wanted that hydrogen. Hydrogen is like the ultimate building block. But the oxygen? They didn't want it. To the bacteria, oxygen was just the wrapper that the hydrogen came in. Once they got the hydrogen out, they just tossed the oxygen aside. We'll get back to that in a minute, because that trash ended up being a huge deal. So now the bacteria had their hydrogen. Next, they took some carbon dioxide. That was just floating around in the water, easy to find. They took the carbon and the oxygen from the CO2, mixed it with the hydrogen they just stole from the water, and they welded them together. The result of all that work was a molecule called glucose. We just call it sugar. This was the breakthrough. Sugar is basically a tiny, portable battery. It stores energy in its chemical bonds. Now, for the first time in history, life could store its own fuel. If the sun went down, no problem. They had sugar stored up. If they wanted to grow bigger or move, they had the energy to do it. They weren't just surviving anymore. They were thriving. They were basically printing their own money. But there was a side effect to this whole process that nobody saw coming. Remember the oxygen? That trash I mentioned earlier? See, when you have millions and then billions and then trillions of these tiny green factories all working at the same time, you start to get a lot of trash. Every time a bacterium made a single molecule of sugar, it spit out a little bit of oxygen as a waste product. It's like how a car spits out exhaust. To the bacteria, oxygen was a toxic pollutant. They didn't want it anywhere near them. It was reactive. It was dangerous, and it basically acted like a chemical saw, cutting through other molecules. So they just dumped it into the ocean. They figured the ocean was big enough to soak it all up. And at first it was. The oxygen would bump into iron that was dissolved in the water, and they would stick together. This created rust. Huge chunks of the ocean floor literally turned red as the world began to rust. It was like a global cleanup crew was taking the trash and burying it in the dirt. But the bacteria kept working. They didn't stop. They were too successful for their own good. Eventually, there was so much oxygen that there wasn't enough iron left to soak it up. The trash started to pile up. The water couldn't hold it anymore. Imagine you're in a room and someone starts pumping in smoke. At first, it's not a big deal. You can ignore it. But after a while, the smoke gets thicker and thicker. It starts to fill the room from the ceiling down. That's what was happening to the oceans. The oxygen was filling up the water until it had nowhere else to go. So it started to bubble out. It broke the surface of the water and escaped into the sky. Before this, the atmosphere of Earth was mostly nitrogen and carbon dioxide. It was a heavy, suffocating place. But now it was being flooded with this new gas. This invisible, aggressive waste product was taking over the world. You have to understand, to almost every other form of life on Earth at that time, this was an absolute catastrophe. Oxygen was like poison gas. It was killing anything it touched. This wasn't some peaceful transition. It was a biological war. These tiny green bacteria were accidentally terraforming the entire planet, and they were killing off their neighbors in the process. But they didn't care. They just kept soaking up the sun and spitting out sugar. They had found a way to win the game of life. They had turned the entire planet into a giant solar power plant.
And in doing so, they set the stage for everything that came after. They changed the color of the sky, they changed the chemistry of the sea, and they prepared the world for a brand new kind of life. The kind of life that didn't see oxygen as trash, but as the ultimate fuel. But before that could happen, the world had to deal with the mess they made. The great oxidation event was underway. It was the first time life had ever changed the planet on a global scale, and it wouldn't be the last. The planet was about to get cold, it was about to get weird, and life was about to find out exactly what happens when you change the rules of the game in the middle of the match.
So life had it pretty good for a long time. It was simple, it was quiet, everything was purple or brown, and the world was filled with these tiny organisms that loved the planet exactly as it was. There was no air to breathe, at least not the kind we like, and the sun was just something that sat in the sky. But then some of these tiny creatures decided to change the game. They didn't mean to, of course. They were just trying to find a better way to eat. These new kids on the block were called cyanobacteria. You might know them as blue-green algae. And honestly, they are the most successful, most dangerous things to ever live on this planet. Before these guys showed up, life got its energy from chemicals. It was hard work. You had to find a volcanic vent or a specific rock and basically suck the energy out of it. It was like trying to live off the crumbs at the bottom of a toaster. But the cyanobacteria found a better way. They figured out how to use sunlight. They took water, took some light, and turned it into pure energy. It was like they discovered a way to print their own money. This was photosynthesis. It's the same thing plants do today, but back then it was brand new.
It was a total revolution. But here is the catch. When you make energy this way, you produce a waste product. You get a leftover gas that you don't need, and that gas was oxygen. Now, to you and me, oxygen is the good stuff. We can't go 5 minutes without it. But 3 billion years ago, oxygen was a nightmare. It was a toxic, reactive, corrosive gas. If you were a normal bacteria living back then, oxygen was basically liquid fire. It ripped apart your cell walls. It trashed your DNA. It was a chemical weapon. And the cyanobacteria were pumping it out by the ton. At first, the planet actually tried to help. The oceans were full of dissolved iron back then. When the oxygen hit that iron, they bonded together. It turned into rust. For millions of years, the ocean didn't get filled with oxygen. It just turned into a giant rusting bucket. All that rust sank to the bottom of the sea, creating these massive red layers of rock that we still mine for steel today. The Earth was basically acting like a giant sponge, soaking up the poison so the rest of life could keep living. But a sponge can only hold so much. Eventually, the iron ran out. There was nothing left in the water to soak up the oxygen, so the gas started building up in the water. Then it started leaking out of the ocean and into the sky. This is what we call the Great Oxidation Event. It sounds like a nice, clean name, but it was really the first global apocalypse. You have to imagine a world where the very air becomes a poison. The old-school bacteria had nowhere to go. They couldn't hide. They didn't have any defense against this stuff. Imagine if suddenly the air you breathed turned into bleach. That's what happened to them. Almost everything on Earth died. It was a total wipeout. The life that ruled the planet for billions of years was scrubbed away because these little green guys wouldn't stop burping out oxygen. But the cyanobacteria didn't stop there. Their success actually ended up breaking the planet's thermostat. See, before this happened, the Earth was wrapped in a thick, warm blanket of methane gas. That methane kept the planet cozy and warm, even though the sun was actually a lot dimmer back then than it is now. But oxygen and methane don't get along. They react. When all that new oxygen hit the methane blanket, it tore it apart. The blanket was gone. Suddenly, the heat from the sun started escaping back into space. The temperature didn't just drop a little bit, it crashed. The Earth turned into a giant snowball. We call it the Huronian glaciation, and it was the longest ice age in the history of the world. We're talking about ice that was kilometers thick, covering the entire planet from the poles all the way to the equator. The whole world was a white, frozen desert for 200 million years. Think about that. 200 million years of solid ice. It's a miracle anything survived at all. So life was in a real mess. If you were lucky enough to survive the oxygen poison, you were now freezing to death under a mountain of ice. The cyanobacteria had won, but they had almost killed the world in the process. They were the victims of their own success. They had changed the atmosphere so much that they made the planet almost uninhabitable for themselves. This is the part of the story where things could have just ended. The Earth could have stayed a frozen, dead rock floating in space. But life is stubborn. While the planet was frozen, a few survivors were hiding in little pockets of heat, maybe near deep-sea volcanoes or under thin spots in the ice. And these survivors were doing something incredible. They were learning how to deal with the poison. They were evolving. Some of them figured out how to use the oxygen instead of just dying from it. They realized that oxygen is actually packed with energy. If you can handle it without blowing up, you can use it to burn fuel way more efficiently than any of the old bacteria ever could.
It was like life had been driving around in a golf cart, and then it suddenly found a way to use rocket fuel. It was dangerous, it was volatile, but if you could master it, you could do things that were never possible before. This shift changed the whole trajectory of life. Before the oxygen, everything was slow, everything was small. But with this new high-energy fuel, life could start thinking bigger. It could start building more complex cells. It could start teaming up. But it wasn't an easy transition. It was a brutal, slow-motion struggle that lasted longer than the time dinosaurs walked the earth. The Great Oxidation Event was a reminder that life doesn't just live on Earth, it shapes Earth. It changes the chemistry of the rocks and the air. Sometimes it changes them so much that it almost deletes itself. The cyanobacteria weren't trying to be villains. They were just doing what life does, finding a way to grow. They just happened to be so good at it that they broke the world. But out of that frozen, poisoned mess, a new kind of world was starting to take shape. The stage was being set for something much more complicated than a single-celled organism. The survivors of the oxygen apocalypse were the ones who would eventually become every plant, every animal, and every human being you've ever seen. They took a catastrophe and turned it into an opportunity.
They didn't just survive the change in the rules. They learned how to win the new game. And that new game was going to lead to the most explosive growth of life the planet had ever seen. But before that could happen, life had to figure out how to do something it had never done before. It had to learn how to work together.
So I just told you that life had to learn how to work together. But before these tiny cells could even think about teaming up, they had to deal with a much bigger problem. They were living through the biggest environmental disaster in the history of the world. You've probably heard people talk about oxygen like it's this great life-giving thing. We need it to breathe, right? We love the stuff. But back then, for the original inhabitants of Earth, oxygen wasn't life. It was a death sentence. It was pure, corrosive poison. Think about what happens to a piece of scrap metal when you leave it out in the rain. It rusts. It literally falls apart because the oxygen in the air is eating it. That is exactly what was happening to almost every living thing on the planet about 2 billion years ago. The world was filling up with this stuff, and it was shredding cells from the inside out. It was a total massacre. Most of the life on Earth just vanished. It couldn't handle the change. It stayed stuck in the mud or hid in the dark corners of the ocean where the oxygen couldn't reach it. For a long time, it looked like the whole experiment of life was just going to end right there, choked out by its own waste. But here is where the story gets interesting. You know how some people can eat spicy food that would make anyone else end up in the hospital? Well, a few lucky cells did something even crazier. While everyone else was dying, these few survivors had a tiny mistake in their genetic code. We call that a mutation. It wasn't planned, it wasn't some grand design, it was just a fluke. But that fluke changed everything. These mutated cells didn't just find a way to survive the oxygen, they found a way to use it. I want you to imagine you're at a construction site. All the workers are using hand saws and hammers. They're working hard, but things move slowly. It takes weeks to build a single wall. That's what life was like before this. The cells were getting their energy from basic stuff like sulfur or heat. It worked, but it was weak. It didn't give them much power. Then, suddenly, one of the workers shows up with a high-powered electric saw and a jackhammer. That's what oxygen was. It was a high-octane fuel that nobody knew how to plug in yet. When these mutated cells started breathing the oxygen, they unlocked a massive power source. It was like they had been running on old AA batteries, and suddenly someone handed them a nuclear reactor. I'm not exaggerating. Using oxygen to create energy is about 15 times more efficient than the old way of doing things. 15 times. Imagine if your car suddenly got 15 times better gas mileage, or if your phone battery lasted for a month instead of a day. You could do so much more. You'd have so much extra time and energy. That's exactly what happened to these cells. Before this, they were tiny and simple because they couldn't afford to be anything else. They didn't have the budget to grow big. Every bit of energy they had went just into staying alive. But now they had a surplus. They had more energy than they knew what to do with, so they started to spend it. First, they started growing. These cells got much, much bigger than the ones that didn't use oxygen. They weren't just tiny specks anymore. They were becoming the giants of their world. And because they were bigger, they could fit more stuff inside them. They could build more complex machinery. They could store more information. They were becoming the luxury models of the biological world. But it wasn't just about getting big, it was about speed. Since they had all this extra fuel, they could divide and make copies of themselves way faster than the old cells. If you have two groups of life, and one group can make a copy of itself every few days, but the other group can do it every few hours, who do you think is going to win? The oxygen users started taking over the planet. They were out-eating, outgrowing, and outpacing everything else. I want you to think about the pressure of this. You're a tiny cell in a world that is literally trying to burn you alive. You're surrounded by the bodies of other cells that couldn't cut it. But inside your own little bubble, you've figured out how to turn that fire into a motor. You're not just surviving anymore. You're thriving. You're the king of the hill. This was the turning point. This was the moment life stopped being a slow, quiet crawl in the mud and turned into a high-speed race. Without this shift, life probably would have stayed as a thin layer of slime on the rocks forever. There wouldn't be any plants, there wouldn't be any animals, and there definitely wouldn't be any people. We owe our entire existence to a few microscopic freaks that learned how to eat poison. It's funny when you think about it. The thing that almost killed life ended up being the thing that saved it. It forced life to get better. It forced it to get stronger. And this extra energy didn't just stay inside those individual cells. It created a ripple effect. When you have that much power, you can start doing things that were impossible before. You can start building more complicated structures. You can start developing better defenses. You see, once these cells had their energy problems solved, they could move on to the next big challenge. They weren't just worrying about where their next meal was coming from. They had the resources to start experimenting. And that's where things get really wild. Because once you have a bunch of big, fast, high-energy cells swimming around in the same place, they're eventually going to bump into each other. And instead of just bouncing off or trying to eat each other, some of them were going to try something new. They were going to stop acting like individuals and start acting like a team. But that only worked because they had the oxygen to power the whole operation. It takes a lot of fuel to run a team. It takes a lot of coordination and a lot of work. But with this new oxygen fuel, the sky was the limit. The engine had become the poison, and that engine was about to start driving life towards something much bigger and much more complicated than a single-celled speck. So you have these fast-moving, high-energy cells everywhere. The oceans are starting to churn with them. They're multiplying so fast, they're covering the seafloor.
They're filling up the water columns. The world is becoming a very crowded place. And in a crowded place, you have to find a way to stand out. You have to find a niche. Some cells stayed small and efficient. Others went for size. But the winners were the ones that took that massive energy boost and used it to change the way they lived. They didn't just stay the same. They evolved. They adapted. And they did it all while breathing the very stuff that had wiped out their ancestors. It's a pretty incredible comeback story if you think about it. One day you're at the brink of extinction, and the next you found the key to the kingdom. And all it took was a little bit of poison and a lot of luck. So how does that luck actually play out? Well, it starts with a massive mistake. Picture two tiny organisms floating around in the water about 2 billion years ago. They aren't much to look at. One is a big, slow-moving scavenger. It spends its whole life hunting for smaller bits of food just to keep the lights on. The other is a tiny, high-energy specialist that's actually really good at dealing with oxygen. Back then, oxygen was basically toxic waste to most living things. But this little guy was different. He could take that poison and turn it into pure power. One day, the big cell gets hungry. It spots the little guy and does what it always does. It moves in, wraps its skin around the small cell, and gulps it down. Normally, that's the end of the story. The big cell would release some chemicals, melt the little one down, and go find another snack. But this time, the system broke. Maybe the big cell was having an off day. Maybe the little cell was just a bit too tough to kill. For whatever reason, the little guy didn't die. He just sat there, trapped inside the big cell, waiting to see what happened next. This is the moment everything changed. Instead of fighting to get out, the little guy kept doing what he did best. He took in the scraps from the big cell and started pumping out energy. It was like the big cell had suddenly swallowed a nuclear reactor. It felt a massive surge of power that it never had before. It realized that it didn't need to digest its prisoner. In fact, having this roommate was a total game changer. The little cell got a safe home where nothing else could eat it, and the big cell got a built-in power plant that never turned off. This wasn't just a fluke. These two became a permanent team. When the big cell split in half to make a copy of itself, it made sure a few of those little power plants went along for the ride. They became part of the family. Scientists have a fancy name for this. They call it endosymbiosis, but you can just think of it as the world's most successful merger. Before this happened, life was stuck in the slow lane. Cells were tiny and simple because they didn't have enough energy to grow. But with this new internal battery, the brakes were off. Think about what you can do when you finally have enough power. You can start building bigger bodies. You can start grouping up with other cells to do complex jobs. This one weird accident created the foundation for everything you see today. Every blade of grass, every bird in the sky, and every human being started right here. We call those tiny survivors mitochondria now. You have trillions of them living inside you right now, still working, still paying rent, and still powering every single breath you take. It is a lot to take in, I know. But when you look at the whole map, the story actually makes a weird kind of sense. It wasn't some magic trick. It was just a really long, really lucky chain reaction. It all started with those boiling rocks at the bottom of the pitch-black ocean. You had hot water hitting cold water and minerals screaming out of the Earth's crust. That created what was basically a natural battery. It wasn't alive yet, but it had a charge. And in nature, if there's energy lying around, something is eventually going to find a way to use it. Those first chemicals started bumping into each other until they formed those fat bubbles I mentioned. This was the first us versus them moment in history. Think about how important that was. The bubble kept the good stuff inside and the chaos of the ocean outside. It was a tiny, microscopic fortress. Inside that protected space, the chemistry could finally start to learn its first real tricks. It learned how to make copies of itself. It learned how to get more stable. It was a simple container, but it was the start of everything. Then some of those cells got brave. They drifted away from the vents and headed up toward the surface. They found the sun. Imagine being the first thing on Earth to realize you could literally eat light. That changed the entire game. Suddenly, life wasn't just huddling around a few hot holes in the ground for warmth. It could spread across the entire surface of the planet. These light eaters started making oxygen as a waste product. They basically filled the atmosphere with the very stuff that makes our lives possible today. They paved the way for us without even knowing it. That leads us right back to that merger I told you about, that moment when one cell grabbed a smaller one and kept it around to generate power. That was the turbo boost. It's what allowed life to get big and complicated. It's why we have trees and dogs and people instead of just a world full of green slime. But here is the part that I still can't get over. Look at your hand for a second, or think about your heart beating. You might think we are these high-tech modern machines, but we aren't, not really. Your body is still using the exact same toolkit that those first bubbles invented in the dark 4 billion years ago. We still use the same salt water in our veins. We still use the same electrical charges to move our muscles. We still use the same tiny engines to turn food into fire. We haven't really invented anything new since the beginning. We just found more creative ways to stack those original building blocks. You aren't just living on a planet that started life. You are a walking, talking version of that original deep-sea chemistry experiment. We are just the latest version of a very, very old trick.